Okay, the streaming has started.
Good afternoon, everyone. Welcome to DAA's Astro Seminar. It is my pleasure to welcome Dr. Fabio Antonini in today's Astro Seminar. Fabio did his PhD at Rochester Institute of Technology with Professor David Merritt. He was a CETA Fellow and a Sierra Fellow afterwards. Now he is a Rutherford Fellow and lecturer at the Gravity Exploration Institute at the Cardiff University. Fabio has diverse research interests in gravitational dynamics that encompasses star clusters, nuclear clusters, galactic center, and even exoplanets. Recently, he has worked a lot on the astrophysical implications of gravitational wave sources. For organization purposes, I would like the audience to post their questions in the chat box during the talk, and I will mention the questions to Fabio at an appropriate time. So thank you, Fabio, for the seminar, and I leave the stage to you.
Okay, thank you, Surab, very much. It's very nice to be introduced by you. Well, me and Surab go back to a few years ago, maybe more than a few years ago, okay, 2014, where we both started our postdoc at Sierra in the US. And at that point, we were both dedicating a big part of our research time to a topic that was, okay, interesting, but not interesting to many people, I would say, gravitational wave astrophysics. And then it was very nice to see that after only 1 year, LIGO actually made the first detection. And I can say now that this topic has become probably the hottest one around. And from that detection, of course, now the field of gravitational wave astrophysics has grown very much and has really changed our understanding of black holes. Here is a schematic view of what we know so far from LIGO. It just gives the masses of the black holes detected by LIGO. And the vertical axis is the mass of the black holes. The LIGO sources are the blue points, the blue symbols. The purple symbols are the here are the black holes that are detected, have been detected in the galaxy through their electromagnetic counterpart in X-ray binaries. Then you have this, what we call mass gap between 2 and 5 solar masses, where there was not really any detection of black hole or neutron star. And then below 2 solar masses, you have neutron stars. And a couple of them that have also been detected by through the gravitational wave radiation, emitted gravitational wave radiation. And you see how from this figure how, for example, LIGO has the LIGO observations have given us information about the mass distribution of the black holes. We have detected black holes that are much more massive than the black holes detected in X-ray binaries, extending again our knowledge about the black hole mass function. And there are other obvious interesting things that have emerged from the observations that, for example, allow us to put constraints on the spin properties of the black holes that are otherwise very difficult to attain. And there are also a few of these sources that are worth mentioning because they're interesting in terms of their and quite puzzling. One source is this source here, GW190814. And you see this is a binary black hole merger, so a merger of an object of 20 solar masses, and the secondary object is about 2.5 solar masses and could be either the largest neutron star that we have ever observed or the lightest black hole that we have ever observed. And in either case would break a record, but it's certainly the first detection of a black hole binary component in this mass gap where previously no neutron star or black hole was observed. And it's interesting also in terms of astrophysical channels for the formation of these sources, because it's very hard to form any system with this extreme mass ratio about 10. So the primary black hole in this source is about 10 times more massive than the secondary. And finally, the last source, binary black hole merger detected by LIGO, 1905-21. This is interesting, as you can see from this plot, because of the very large mass. So this is the highest mass binary we have observed so far. And also it's interesting, as before, because it's very challenging, again, to explain this in terms of astrophysical formation channels. At least the primary black hole mass has a mass of around 80 solar masses, which is much larger than you would expect based on simple stellar evolution models. Of course, just in tomorrow, LIGO will release the new catalog of gravitational wave sources that will change drastically this picture. And eventually we will detect hundreds, thousands of gravitational wave sources of binary black holes, and we will be able to address really key questions about both black holes and stars. And of course, one of the first questions that we would like to address, well, the most obvious one, is how do merging black hole binaries form? How? So only by first answering this question, we can then we will then be able to answer fundamental questions about the astrophysical environment where these objects have been formed. And this include both binaries, the evolution, so will give us information about the evolution of massive binaries in the field of galaxies, or maybe the evolution of multiple star systems in the field. And one possibility that I will explore in this talk. So my talk will be mostly focus on this alternative scenario for the formation of these sources. Is that they form through dynamical interactions in dense star clusters, and this could be globular clusters, nuclear clusters, and open clusters. But in this seminar, I will mostly consider globular clusters, and then spend the last 5 or 10 minutes on this other type of stellar systems, nuclear star clusters. So how black hole binaries form in a dense star cluster? Well, I will give you just a schematic representation of all the processes that go into this formation channel. Well, you start from your star cluster. The most massive stars in the star cluster, they evolve and form black holes. The black holes that are produced by these stars are typically between 10 to 50 times more massive than the stars in the field. And so as they in the cluster, so as they interact with these stars, because during these interactions they tend to reach equipartition of energy, they lose specific kinetic energy. The black holes lose specific kinetic energies in these interactions, and the stars are accelerated and gain specific kinetic energy. So the stars will tend to move away from the core, while the black hole, by decelerating, sink to the center of the star cluster through a process which is called mass segregation. The key dynamical process that actually leads to mass segregation is dynamical friction, is deceleration. This deceleration suffered by the black holes as they interact with the lighter stellar component. And this process was first discovered by Chandrasekhar in the 40s, and it's probably his most important contribution to stellar dynamics. And it's also the key ingredient that leads to the high densities of black holes in the core of star clusters that eventually allow three-body binary formation processes to take place and to form black hole binaries. So because of the high densities of black holes now in the core of the star cluster, black holes take part in frequent three-body interactions. These are interactions that can involve, for example, a binary and a single black hole, where the single black hole during the, after the interaction replaces, as a consequence of the interaction, replaces the initial star in the binary, and then you form a black hole binary. But actually, the most important type of interactions are these three-body binary formation processes, where you have three black holes that are initially unbound from each other. They interact closely in the core of the star cluster, and then after the interaction, you form a binary with the third black hole that is ejected from the system, carrying away the energy that is needed in order to bind the remaining two black holes. A fraction of these binaries that form through three-body processes are hard, which means that as they interact with surrounding mostly black holes, with the other black holes in the cluster core, they become even harder. So their semi-major axis shrinks in time. And because of conservation of energy, linear momentum, you can conclude that every time there is an interaction, the center of mass of the binary also must receive a recoil kick. And you can show that for systems with an escape velocity which is less than 50 kilometers per second, so most globular clusters actually, a large fraction of these binaries will be ejected from the star clusters before they merge. So a large fraction of the binary black hole mergers that are produced in globular clusters actually are produced early on during the evolution of the cluster. They are ejected and then they merge eventually after many gigayears from their formation in the local universe. Of course, another possibility, which I will describe more in detail later, is that the binary actually merges in between one of these binary single interactions inside the star cluster. But eventually, this binary will, because of the anisotropic emission of gravitational wave radiation, will receive what we call a relativistic kick, which can be several hundreds to thousands kilometers per second. It will be most likely also ejected from the star cluster. And so through this process, dynamical processes, the cluster gets rid of all a large fraction, at least, of its black hole population. So the key questions that we like to address now is, well, what's the merger rate and what are the properties of the black hole binaries that are formed dynamically in dense star clusters? What are the theoretical error bars that are associated with this formation channel? And there are a number of difficulties that must be considered when doing this. First, the study of cluster dynamics requires really expensive simulations based on Monte Carlo or N-body techniques. To give you an idea, in order to simulate the evolution of a very massive cluster, like a 10 to the 6 solar mass cluster, then a Monte Carlo code would require maybe 1 week, about 1 week of computational time, even on a computer cluster, and an embodied code would require even 1 year of computational time. So this is very expensive. And the other key is that we don't really know the cluster initial conditions. We don't know the cluster initial mass function, and we don't know their initial properties as formation. And so in order to really address the theoretical error bars associated with this process of black hole binary merger formation, we need to explore a very large portion of parameter space, and in which translates in with the need of running millions of cluster models in order to properly address the merger rate and place theoretical error bars on these estimates. And so because of this, we developed a new code, which we call cluster BHP dynamics, or in short, cBHBd, which is a fast cluster code that allows you to make predictions for the evolution of a cluster and the black hole binary mergers that it produces in just in less than 1 second. And this code is based on what we call principle of balanced evolution, which is due to a non. Okay, so first think about a cluster that has no binaries. Okay, so the cluster core, we will find that the cluster core will tend to contract, while the outer layers, the rest of the cluster will tend to expand because of dynamical interactions. But this process is usually referred to core collapse, and core collapse is a process that leads to infinite densities in a finite time. But in reality, these infinite densities cannot be achieved, and that cannot be achieved because at some point the densities become large enough that binaries will start to form through three-body processes, and binaries will inject energy into the core and will halt this core collapse process. After this time, the cluster will exist in a state of what we call balanced evolution, in which the energy generation rate in the core by binaries is regulated by the energy demand of the entire system. So it's the rate at which binaries interact with stars and produce energy is really set by the global properties of the cluster, and does not really depend on the details of the small-scale dynamics that take place in the core, which is the type of, so we don't need to follow the small-scale dynamical interactions that really carry a high computational cost. And I like to make the analogy here with stars. So in stars, what sets again the energy production rate by nuclear reaction again is actually the structure of the global properties of the star, like the mass and radius of the star, and the core will have to adjust its properties such to meet the energy demand from the entire system. And in a star, what sets the luminosity at the surface is the maximum amount of radiation, of energy that can be transported from the core throughout the stars through radiation. Okay, while in a star cluster, of course, you don't have radiation, but you have two-body encounters, and so we can say that the maximum energy that can be produced by binaries, the energy production rate by binaries, this E dot, is set by the maximum amount of energy that can be transported from the core to the rest of the cluster through two-body encounters. Mathematically, this means that the energy production rate by binaries is proportional to the total energy of the cluster divided by the relaxation time, where the relaxation time is simply the time scale over which random gravitational wave encounters change the orbits of stars significantly. So by this simple argument, what we need to know is just the evolution of the global properties of the cluster, like its mass and radius, and from there we can compute the binary hardening rate. So the two are related, and from the binary hardening rate we can simply compute the binary merger rate without carrying any expensive cluster simulation. And so we use these equations to describe the evolution of the cluster mass due to stellar evolution, for example, the black hole mass, and so this is just the mass, the total mass in black holes in the cluster, and the radius of the cluster. And you will see that, you see here that these equations are depend on some parameters, nu, beta, and zeta, which we find by fitting the results of n-body simulations. Okay. And so in order to actually compute a merger rate and the properties of the black hole binaries that are produced in these interactions, we need to specify what type of interactions we're talking about. So as I said before, these are three-body interactions involving binaries and a single binary black holes and single black holes mostly. And here you see one of these, an example of one of these interactions where you have a single black hole again that interacts with a binary. And the point here is that in these interactions take are very complex and take many orbital times to complete. The other important point is that you will see at the end of the interaction the new binary that is formed. The motion of the two black holes in the new binary is much, so they move much faster than in the initial binary. And this orbital energy is given up in form of kinetic energy to the black hole that has been ejected from the interaction and to the center of mass of the binary. So eventually, because this recoil kick suffered by the binary increases as the semi-major axis of the binary, as the binary shrinks, there will be a given semi-major axis, let's say A ejection, at which the binary can be ejected from the star cluster. And so we identify this first type of mergers that we call ejected mergers. So these are binaries that are ejected after, that merge after being ejected from their parent cluster. And then we have other two types of mergers that we consider. We consider two-body mergers. So these are mergers that occur in between two interactions. So after one binary single interaction, the semi-major axis and the eccentricity of a binary can be such that the binary merger timescale becomes shorter than the timescale for the next interaction to take place. And so these binaries will merge inside the cluster. And then we have this third type of mergers that we call three-body mergers or gravitational wave captures. These are a very small fraction of all mergers produced in star clusters, but they're very interesting because they are the only type of mergers that we consider, at least, that can produce eccentric binaries in LIGO. And these systems are systems in which the two black holes merge during a binary single interaction. We have seen that these interactions are often chaotic, and so two black holes can sometimes come so close to each other that they are driven to a merger before the interaction is completed. Because this, in order for this to occur, the separation between the two black holes has to be very small, then this results in binaries with extreme eccentricities. In order to compute the merger rate associated with each of these channels and the properties of these sources, we make a few assumptions. We assume that the distribution of eccentricities of binaries that emerge from this interaction is thermal, which is well documented by n-body simulations of scattering experiments similar to the one I showed you before, which says simply that the number of binaries with an eccentricity that is less than E is proportional to E squared. We are neglecting weak encounters that we think have about a 10% effect on the merger rate and the properties of the binaries. And finally, we assume that the three black holes taking part in each of these interactions have the same mass, and that this mass is equal to the mass of the largest black hole that exists at the point in the cluster. All these assumptions are reasonable when we look at the results from more complicated and expensive but more detailed simulations of star clusters. So in this slide, you see the comparison between our fast cluster models to the results of n-body simulations of star clusters. The upper panels give the evolution of the cluster mass, radius, and the mass of the black hole population. And the point is that the models, our models, reproduce the results of embodied simulations very well. But well, this is not really surprising because, as I explained before, the evolution of our cluster models is regulated by a set of parameters that are fit to the results of embodied simulations. What is surprising, well, or remarkable, if you want, is the lower panel, which shows the binary black hole merger rate for this specific cluster model as a function of time, compared to the results from a star-by-star Monte Carlo simulation of a globular clusters from Rodriguez et al. 2018. Also, Surab contributed to this paper. And it is remarkable that our simple model reproduces so well the binary black hole merger rate found in these simulations. So this is encouraging, and I will continue now with this comparison between our models and published Monte Carlo models of dense star clusters from Rodriguez et al. In the upper panel, you see the fraction of mergers produced by star clusters as a function of the initial cluster mass. For the three population of mergers, ejected binaries in clustering spirals and gravitational wave captures, you see that ejected binaries represent more than 50% of all mergers. In cluster mergers are about 30, maybe up to 40% of all the mergers, and gravitational wave captures again represent only a few percent of all the mergers. But the point is that, again, our models do a pretty good job at reproducing the results of the detailed simulations from Rodriguez et al. And in the lower panel, you see the number of mergers per cluster, again, as a function of the initial cluster mass. And again, the agreement is quite good, although we might be underestimating the number of mergers at the lowest cluster masses. This plot shows we can also make predictions for the eccentricity of the sources. So we do also a comparison about the eccentricity distributions here, which are plotted at different time after 3, 5, and 8 gigayears from the formation of this particular cluster model. And you see again that the match between the fast models and the Monte Carlo models is very good, with maybe only 10% of all sources having an eccentricity is larger than 10 to the minus 2 in LIGO. So this is the cumulative eccentricity distribution of the black hole binaries when they enter the LIGO frequency band. And in the lower panel, you see the distributions for the three types of mergers ejected in clustering spirals and captures, and you see that all the eccentric mergers are again gravitational wave captures, both in clustering spirals and ejected have eccentricities typically that are too small to be measurable in LIGO. But again, one of the points I want to make here is that again the match between Monte Carlo models and our fast models is very good. So now that we are confident that our code work, we can proceed and look at what and to look at making predictions about the properties of the binary black holes that are formed in star clusters. And I will look specifically, or at least firstly, to the case of globular clusters, and then, if time allows, I will also look at nuclear star clusters and explain why I think this other type of systems are also very interesting. So this is the rates equation that we use to compute a merger rate for binary black holes formed in globular clusters. The first term in the right-hand side, in the first term you have the rho, so the mass density of globular clusters in the universe, rho GC. Globular clusters lose mass in time because of dynamical process and stellar evolution. So their initial density, mass density, was maybe much larger than it is today. And so we have to take this into account when we estimate the merger rate. And it turns out that this is actually one of the main uncertainties in this calculation. We don't really know how much mass was lost by globular clusters until the present time, and we don't know the initial globular cluster mass function. And uncertainties in, this is important to know that uncertainties actually on this parameter were essentially neglected until our paper. So in the literature, you will see that the uncertainties related to the 2K, so to the fractional mass loss of globular clusters have been neglected. But again, they represent one of the main uncertainties for this channel. And so K times rho GC is just the initial globular cluster mass density per mass density, and divided by the initial globular cluster mass gives you a number density of globular clusters. We multiply this by the average merger rates of binary black holes per cluster over a sample of models to obtain the merger rate at a given redshift. So in order to compute this equation, what you need to know is, again, the globular cluster mass density today, this rho GC. You need to know the initial globular cluster mass function, which is unknown, but I'll show you how to derive this in order to be consistent with what we know about globular clusters. And the initial globular cluster mass function, of course, enters both in this part of the equation because we sample the masses of our clusters from this, but also enters here because once on the calculation of K, because once we compare it to the current globular cluster mass function, we can determine how much mass has been lost from clusters to the present time. And finally, there are uncertainties that are related to the initial globular cluster properties. We don't know what's the initial density of globular clusters, and we don't know very well how massive stars evolve, which translates in uncertainties in the stellar evolution prescriptions. And I think Surab was maybe the first actually to point out that these uncertainties could be very important when, or not, when estimating the binary merger rate from this channel. So let's look at the first two things. So the essentially the we want to know the initial cluster mass density, which is the globular cluster mass density today multiplied by the fractional mass loss of globular clusters over their lifetime. So the globular cluster mass density today is obtaining such that it is to be consistent with its empirical value. So and this is done in the following way. So in observations show that this is quite remarkable, that the globular cluster mass in galaxies is a constant fraction of the dark matter halo mass. And this is true for a wide range of halo masses. And so we can say that the mass density of globular clusters is some fraction of the dark matter halo density, mass density in the universe. And of course, there are some uncertainties related to eta, which we also include in here. Now, in order to compute K, or if you want the initial globular cluster mass function, we require this to be consistent with the observed mass function of globular clusters in the Milky Way. So we don't know the initial globular cluster mass function. What we know is the globular cluster mass function today. And so we start from there. We say that today, the globular cluster mass function can be fit by this function of 4, which we call a evolved Schechter mass function, in which we assume that clusters all lose an equal amount of mass during their lifetime, delta. Delta is the amount of mass lost by from globular clusters by any process, which could be to body relaxation, shocks, or evaporation in a tidal field. And m star is a sun truncation mass above which the mass function decays exponentially. And so you can show that in a model in which half of the mass is initially lost by stellar evolution, so in the early stages of their evolution, clusters lose approximately half of their mass through stellar evolution processes, such as stellar winds and supernovae. So in a model in which clusters lose half of their mass by stellar evolution, and then they lose an amount of mass delta during their lifetime, this globular cluster mass function translates into an initial globular cluster mass function, which is simply a power law mass function with slope -2, which is truncated at 2 m star. And so what we do is to feed through an MCMC procedure the globular cluster mass function today to recover posterior distributions for these parameters m star and delta. And so practically what we do is we take 100 values from these posterior distributions, and for each of these values we run a sample of clusters from which we derive a merger rate estimate. And this way, we not only can determine an estimate for the merger rate, but we can also first include these uncertainties in the estimate, so determine error bars and theoretical error bars, and end up actually with a distribution of merger rates, as I will discuss next. Of course, there are other uncertainties that we take into account. We can, again, consider variations in these uncertainties just because of our new code that allows us to explore a much wider range of parameter space than was possible before. So we changed the, in the next, I will actually show models where we only change the cluster initial density and fix all the other parameters, because it turns out that actually the cluster initial density is the parameter that affects the merger rate the most. Again, we don't know what the initial cluster densities are, so we just assume here that clusters have initially all the same density that changes between 10 to, this should be 10 to the 3 to 10 to the 5 solar masses per cubic parsec. So these are finally the results. The upper panel shows the merger rate as a function of redshift for models that start in which clusters have a density of 10 to the 3, 10 to the 4, and 10 to the 5 solar masses per cubic parsec. The middle panel gives the mass distribution of the black hole binaries that merge in the local universe. This is the primary black hole mass. And the lower panel gives the distribution of the globular cluster masses for the globular clusters that actually produce the black hole binaries in the local universe. And for example, you see that most of the binary mergers in the local universe come from clusters with a mass around 10 to the 6 solar masses. So let's focus now on the upper panel. The point, so the dashed lines here are the uncertainties, okay, the 90% confidence bands associated with each merger rate estimate. And you see that within these uncertainties, our merger rate estimates are in quite good agreement with the merger rate inferred from the LIGO observations, which is about 40 per cubic gigaparsec per year, but this again will change in just 1 day or so. And so we conclude that a model where most of the black hole binaries detected by LIGO actually come from globular clusters is consistent with current constraints. The second point I want to stress is that only the highest density models actually can reproduce this merger rate value, are consistent with the inferred merger rate values, and they also actually provide a better match to the inferred black hole mass distribution. So the high density models provide a much, if you look, for example, at the low density models, the mass distribution of a slope that is positive or flat, while observations show that the slope should be negative. So there are, again, this is more consistent with models that start with a high density, above 10 to the 4 solar masses per cubic parsec. So high density models, again, give a better match to the inferred merger rate as well as the black hole mass distribution, which I think is very interesting. Again, for each, because we have a distribution of initial cluster mass functions, we can compute for each of them a value of the merger rate and the evolution of the merger rate with redshift, which we fit within redshift 1 with this functional form here, where R0 is simply the merger rate in the local universe, and lambda is a slope that parameterizes the evolution of redshift of the merger rate with redshift. And so we can derive a posterior distribution for these parameters, lambda and R0. And you see again that these are, so the binary black hole mergers in globular clusters contribute about 7, a merger rate that is about 7 per cubic gigaparsec per year, and lambda is about 1.6. Again, these are actually pretty consistent with what we find with LIGO. Also, through with our code, we can look at different type of mergers, as I explained before. And the interesting result here is that if you look at in-cluster mergers, what you find is that the merger rate from in-cluster mergers and gravitational wave captures does not really depend much on the initial cluster density. So it's quite independent on the initial conditions. And so we conclude that the merger rate of gravitational wave captures, or if you want, eccentric binaries in LIGO, is independent of the initial condition, and it is about 0.4 per cubic gigaparsec per year. I'm talking, of course, about the merger rate in the local universe. And you see also that the in-cluster mergers that are represented in the middle panel with these dashed or dot-dashed lines have the much lower masses than the ejected binaries, and are produced by the most massive globular clusters with masses above 10 to the 6 solar masses, which is also quite interesting. Now let's look at other variations in the model. We don't really know we don't have a very good description of how metallicity evolves with redshift, so we changed this the metallicity of our cluster models. We changed the supernova mechanism and the further black hole mass distribution. We changed also, we consider different prescriptions for the formation time of globular clusters, and also for the natal kicks of the black holes. And the main point I want to make here is that, so if you look at only at the upper panels, and within redshift 2, the merger rate and merger rate evolution from all these flavors of these models are quite similar. So the merger rate and its redshift evolution are quite independent on variations of these other uncertain parameters. But of course, these other parameters affect the mass distribution of the black holes and the mass distribution of the globular clusters that produce the local mergers. And so the last conclusion from this work is that the binary black hole merger rate is not much sensitive to these other uncertain parameters in the model, such as natal kicks, black hole masses, and the globular cluster formation time. And why is this important? Well, it's important because then you can think, for example, of about constraining the initial cluster density, which is actually one of the only parameters that affects the merger rate, by using gravitational wave observations. And this is just an attempt of doing this in this plot. So you have in the left panel, the value of R0, R0 for different values of the initial cluster density. And you see that only models that have an initial density larger than 10 to the 4 are consistent with reproducing the LIGO merger rate. And so if we were able, for example, to tell how many of the binaries observed by LIGO are formed in globular clusters, then this could be used to put constraints on the initial conditions of star clusters. So in the last 10 minutes or so, I will describe some work I did on nuclear star clusters and why these are interesting systems in terms of gravitational wave sources, and specifically for the most massive black holes that are formed in the universe, such as 1905-1. So nuclear star clusters are the densest and most massive star clusters that are observed in the local universe. There is one sitting right at the center of our galaxy. In the left panel, you see here the density and effective radius for all type of clusters and galaxies, and you see that. So the gray dots are globular clusters, and these square symbols are nuclear star clusters. And you see the nuclear clusters actually have densities that are a few orders of magnitude larger than the densities in globular clusters, and many orders of magnitude larger than the densities in the mean field of galaxies. So again, they are the most massive and densest star clusters that we observe, and because of this, they, as we show here in this paper with Fred Rasio, their escape velocities are much larger than the escape velocities from globular clusters. Because of these very large escape velocities, because of these very high densities. It is likely this happens in about 20% up to 80% of the cases, depending on the initial distribution of spins of the black holes. It can happen that the merger remnant is not actually ejected from the star cluster by the gravitational wave recoil kick, but it sinks back to the cluster core. It exchanges in a new binary, forms a new binary with another black hole. That will merge again, and this process can repeat several times, leading to substantial growth. And it was already noted back in our paper, and then also shown in this paper by Gerosa and Berti, but there are many other papers that came after these two that show that black holes produced by hierarchical mergers have a different distribution of mass. Of course, they're more massive than first generation black holes produced by stellar evolution processes. They have a different redshift distribution because they merge later on compared to first generation black holes, and they also have a different spin distribution. Because they so once you merge two black holes, the remaining the merger remnant, the remnant black hole has a spin that is about, on average, about 0.7. So even if the two black holes are have initially very small spins, the product of their merger will have a large spin. So this black holes formed by hierarchical mergers are expected to have, on average, larger spins than first generation black holes. So we look at this channel, hierarchical mass growth channel, through our models, and what we plot here is the maximum black hole mass that you can form in our models as a function of the initial escape velocity from the cluster. And this plot, you can see this plot here for different metallicity values and different assumptions for the initial black hole spins. For example, here they range from 0 to 1. Here they are all set to 0. But the interesting point result here is that only and independently on these other assumptions about the stellar populations only for clusters that have a escape velocity larger than about 300 kilometers per second. Hierarchical growth can happen and lead to the formation of black holes that have masses of several hundred solar masses up to a few thousands solar masses. We find that for these conditions, growth actually can occur in less than 10 gigayears, but for reasonably high cluster densities actually can occur on very short time scale, less than 1 gigayear, and might also provide an explanation for the massive black holes that are observed at high redshift. This is simply a zoom of this region of parameter space with that corresponds to escape velocities less than 300 kilometers per second, which are more relevant to globular clusters. And you see that in this case, well, the maximum mass that you can form in a star cluster through this repeated merger process depends very much on the assumptions about the spins of the black holes and the metallicity, but you really cannot form anything above 150 solar masses. So it will be hard to explain a source like GW 1905-21 with this in systems that have an escape velocity less than 300 kilometers per second, at least initially, which would imply in most globular clusters, these sources are difficult to make. So the question is whether there are actually nuclear star clusters that meet these conditions. And what I show here in this plot is the effective radius of nuclear star clusters. This is just the radius containing approximately half of the integrated luminosity of the cluster as a function of the total cluster mass. And according to our models, the region in this plot below these red lines is the region where hierarchical growth can actually happen and lead to the formation of these very massive seeds. And we find that in 10% of nuclear clusters that observe today, conditions are such that we would expect growth to occur. The other condition is that, of course, these clusters contain a black hole population, and also I didn't mention before, but some nuclear clusters, maybe most of them, have a supermassive black hole at their center, which would suppress all these dynamics. So this would be should be taken into account. And we estimate a detection rate of binaries with masses above 100 solar masses of about 1 every a few years, which is again consistent with the detection of the recent source 1905-21. So these are my conclusions. I've shown that it is possible to model dense star clusters and make predictions for the black hole binaries produced by these systems in less than 1 second using our code. I've shown that a model where most of the black hole binaries that are detected by LIGO come from globular clusters is consistent with the merger rate estimates from the gravitational wave detections. We also derived a posterior distribution for the local merger rate and the parameter lambda that determines its evolution with redshift. And we have found, in agreement with previous studies, that the local merger rate is actually not sensitive to the other uncertain parameters in the models, which instead affects other formation channels, like formation in binaries or in triples. And I have concluded by discussing the possibility that hierarchical mergers in nuclear clusters lead to the formation of black hole seeds with masses up to a few thousand solar masses. Thank you.
Thank you, Fabio. I will clap on behalf of everyone.
Thanks.
We can have questions now. I have a couple. Why gravitational wave captures do not depend on the cluster mass? That was not really clear.
Yeah, so, well, I didn't explain why. But yeah, so they don't depend on the cluster density, because so they're produced inside the clusters locally, and after some time, because of relaxation, the clusters, so clusters, even if you start them from very different initial conditions, evolve to the same density. Okay, and so they will have similar properties in the local universe, and this is also one of the reasons why we don't really we cannot constrain the initial globular cluster densities, because even if you start from very different initial conditions, from very different initial densities, they tend to evolve by relaxation to the same density after a relaxation time. And so we find that because of this, in cluster mergers that depend on the current properties of the clusters, the properties of the clusters at that time don't depend much on the density where you started from. While, of course, ejected binaries do, because they're mostly, or at least a large fraction of them, are produced early on, where you had very different initial conditions.
Another really interesting thing was the apparent peak in the merger rate as a function of your rho zero. So can you explain why that peak is coming?
The peak of the merger rates?
Yes.
Sorry, can you say again?
So there was a figure you showed. So it was, I think the rho zero is the x-axis, and the merger rate is the y-axis, and at the top, yeah, this one. Yeah. Why is there a peak?
Yeah, so there is a peak because so if you go above some density, you get so you start merging a lot of your black holes early on in the evolution of the cluster, and so this is the merger rate in the local universe. So by increasing the density above a certain value, you start making a lot of mergers very early on, because the densities are very high, and the binary black hole production rate also increases with the density, the initial density, and so you just don't see them in the local universe because they merged early on. And yes, I agree, this is very interesting, because you know, if you kept going up, then the constraint would be weaker. Although, of course, then cluster densities above 10 to the 7 are solar masses per cubic parsec are not really realistic densities. But yeah, so the reason is that, again, for the largest densities, most of the mergers occur start to happen before you enter the LIGO observable volume.
Yeah, this is really interesting, because there is also a mass dependence that's also peaked. So if you go to very high masses, then the mass segregation time scale becomes too long, and that can limit your merger rate in the local universe. And if you go to very low mass n, then you just you eject most of them with very wide separation, and they don't merge in the local universe or within the Hubble time. Really cool.
Yeah.
So, Goku?
Okay, a very nice talk. I have a question about, I have a couple of questions. So, so this is about the capture binaries you talked about. So even so, you are you still need a 3-body kind of a capture, right?
Yeah.
But in principle, I've been telling this to Saurav too. It's possible that you can actually hyperbolic capture too, especially when you are talking about high density scenario. That is a possibility. And do you worry about those?
Yeah. Well, we don't include them, but in our models. But you're perfectly right that so there is the possibility, and this is especially important for nuclear clusters. Maybe not as important for globular clusters.
Correct. It's
but yeah, so there is the possibility that two black holes now that are unbound from each other interact closely, and then they become bound because energy is lost by gravitational wave radiation, and then they merge inside the cluster as well. And these mergers will also be very eccentric. Yes, so there is a paper, a recent paper from I think Johan something that shows that these mergers can contribute again at the percent level. So it's not going to change the merger rate estimates from our channel, but can increase the number of eccentric mergers significantly.
That's right. Yeah, that's right. Again, the question then, it actually can also depend on the spin. There's another mass. I mean, that comes. So where the merger occurs, where the capture occurs, that's going to be a function of your impact parameter, and that actually can have Newtonian implications. So we are just trying to figure it out what's going on there. I have another thing about you just mentioned that your rate estimate for more than 100 solar mass is sort of consistent with the famous 1905-21 event. But now there have been some independent analysis done on the LIGO data by Alex and Colin. Anyway, they are not part of the LIGO, they were part. So their argument is that unfortunately we did not bother to provide a wide prior for the individual masses or the mass ratios. So they claim, I went through the paper, seems to be fairly convincing, that when you allow the prior to go wider, then the most likely scenario, I mean, it's not unique, obviously, mass ratio around 10, but something like 170 or 15 or something like that, two components. That is typical in your nuclear scenario, cluster scenario, right? High mass ratio?
Yeah, I think it's actually more consistent with our scenario, this picture, because most of the mergers that we produce have a high mass ratio. So once you start growing a black hole, it's very hard to make another one.
Okay, I'm sorry, I got it the other way. Yeah, I mean, so it's a high.
So, but our constraints on the mass ratio are not as good as the constraints. So the predictions that we can make are not as robust as for the total mass of the binary, because of this is quite technical, but so our models make an assumption for the initial for the mass ratio of the binaries. We assume that they have at least in the globular cluster models, we assume that they have equal mass, but we don't consider hierarchical mergers. For the nuclear cluster models, we make so the assumption that the largest black hole is merging always with the second largest black hole in the cluster. But even so, the mass ratio distribution is not really of the hierarchical mergers. Black holes produced by hierarchical mergers is not really peaked around 1. But I still have to check whether this is consistent with. I see your point. So they are claiming a very high mass ratio. So I'm not sure I have an answer for whether our models are fully consistent with this very high mass ratio. But certainly, the distribution of masses of black holes produced through hierarchical mergers is at some point becomes skewed toward low mass ratios.
Comparable masses.
The
dynamical friction argument, right? Because you.
I mean, I have to say, yeah, so we have this, this plot was made about 1 year ago, and we were not specifically thinking about this source, but so I have to go back, look at the data and see whether, also this slide, I have to say, was prepared a while ago, but I have to go back and look at the data, whether, high mass ratio could be consistent with what we find.
Okay.
A related comment about this related thing, high mass ratios. So, what is the black hole mass from given some progenitor mass is quite uncertain, right? And so for a very long time we have been thinking about hierarchical black hole mergers, and that's how we can grow black holes, and maybe the mass ratio will be much smaller and so on. It turns out that maybe you can merge stars before they can become black holes, and then this pair instability supernova limit may not be applicable. So this is, I think Michela Mappeli's group proposed this first. And in principle, you can have very high mass black holes created through mergers that did not involve black holes per se. And then the problem of retaining the merger products will be less severe. Right?
Yeah, okay. Because the kick will not play, okay.
Yeah.
So finally, you just mentioned that, unfortunately somebody came in, so I you mentioned that, it's fairly easy for you to make black holes of 1,000 solar mass or something towards the end. You might have missed it altogether. So the seed black hole can have, 1,000 solar mass or something like that. There was a slide like that. I did not.
Yeah, so this one.
Okay.
Yeah, so the point was that if you go to very initially high escape velocities that are typical for nuclear clusters, we know many nuclear clusters with escape velocities larger than 300 kilometers per second, then, well, at least 10% of them, then you find that this hierarchical merger process will produce black holes above 1,000 solar masses. So that was the point of this.
Okay.
And another point is that this doesn't really depend too much on the initial assumptions for the black hole spins and the metallicity of the stellar population from where you start from.
Okay, so most of this, as a side remark, you will need LISA and maybe third generation detector, watching the same binary kind of coming from one to another, to constrain all these things beautifully. Maybe somebody should worry about how better all these things can be constrained in such a scenario.
Yeah, this is definitely a very good point that maybe I should have mentioned. If there are 10% of nuclear clusters today that have the right properties to make this happen in the past where densities were higher, then probably this scenario would be even more likely. And so looking at high redshift would be definitely very, very interesting. And yeah.
Thank you.
Thank you.
All right. Let's thank Fabio again.
Thank you very much.
Thank you, Fabio. So we will wrap up this session here. It was great seeing you, Fabio.
Yeah, great seeing you. Bye, Saurabh.